Good morning students, this is M. Prasad Raju, stand before you to continue the applied physics classes of Unit 5. The name of Unit 5 is Magnetism. In this unit, my dear students, I would like to explain the terms of basic definitions related to magnetism. The first one is magnetic dipole. Let us see what is magnetic dipole. Magnetic dipole is defined as a system consisting of equal and opposite magnetic poles separated by a fixed distance is called magnetic dipole. For example, if I have a magnet like this and the length of this bar magnet is denoted by say some 2L, and it will have two poles, one is north pole and other one is south pole. If you are going to consider a bar magnet like this, whose length of the bar magnet is considered as 2L, and this L is called magnetic north pole and this S is called magnetic south pole. Now, how to define this magnetic dipole? A magnetic dipole is a system, and a system consisting two equal and opposite poles, let them denoted by north pole and south pole, which are separated by a fixed distance of length of bar magnet is 2L. Then we are going to call such a dipole is said to be magnetic dipole. The second one is magnetic dipole moment. This magnetic dipole moment is denoted by P bar, which is a vector quantity, and it is defined as the product of length of the bar magnet 2L with the pole strength of the magnet. That means, if you consider that this is a bar magnet, the pole strength of north pole is denoted by say some small m. That means, the product of magnetic pole north pole strength with the length of bar magnet is called magnetic dipole moment. It is denoted by P bar. So, in mathematical notations, how do we define this magnetic dipole moment? My magnetic dipole moment P bar is equal to m into 2L. That means where m is equal to magnetic north pole, and 2L is called length of the bar magnet. Length of the bar magnet. This is what is known as the magnetic dipole moment. So, strictly speaking, magnetic dipole moment P bar is a vector quantity. When do we say that a physical quantity is said to be a vector? A physical quantity will have both magnitude and direction. We can call it as a vector. So, ultimately, the magnetic dipole moment is called a vector quantity and it is denoted by P bar. We can write it in mathematical analysis that P bar is equal to m into 2L, where m is called magnetic north pole and 2L is equal to length of the bar magnet. If you want to measure the units of magnetic north pole strength, the SI unit of magnetic north pole strength is ampere meter. Ampere meter, and length of the bar magnet is denoted by meters. So we are going to measure length of the bar magnet is measured in meters, and the magnetic north pole strength is denoted by ampere meters. Okay. Now, strictly speaking, the magnetic dipole moment is related to magnetic dipole. If you see magnetic dipole and magnetic dipole moment, they both one another are interlinked definitions. Now we are going to enter into the third definition, which is called magnetic field. Let us see now. Magnetic field, we also call it as magnetic induction field strength. This is denoted by B, which is called the definition of magnetic field is defined like this. The region in which the magnetic lines of force that can be extended with the influence of magnetic field, I am calling it as magnetic field induction field strength or magnetic field, which is denoted by B bar. I am writing the definition here. The region the magnetic lines of force that can be extended where its influence felt is called magnetic field. This we can also call it as magnetic field strength. So how do we define this, my dear students? If you are going to take a mathematical representation, my magnetic field B is equal to phi by A. Strictly speaking that my phi is called magnetic flux, A is called area of cross section. If you take SI unit of magnetic field strength or magnetic field B bar, I can represent that Weber per meter square. So this Weber per meter square is the ultimate SI unit of magnetic field strength and it is a vector quantity. As you take this B is equal to phi by A, I can represent that the B is called magnetic field strength, phi is called magnetic flux or magnetic flux density, and A is called area of cross section. So in SI system, my phi is measured in Webers. That means the magnetic flux is measured in Webers and the area of cross section is measured in meter square. After finishing this definition of magnetic field, now we are going to enter into the magnetic flux density. Let us see this. The fourth definition is magnetic flux density or magnetic flux. It is denoted by phi. My magnetic flux means, how do we take this? The total number of magnetic lines of force crossing a unit area of the surface is called magnetic flux and it is denoted by phi. So I am writing the definition here. The total number of magnetic lines of force, the total number of magnetic lines of force crossing unit area of the surface is called magnetic flux. It is denoted by phi. It is denoted by phi. How do we represent this magnetic flux in mathematical representations? I am taking phi is equal to B into A. So there is a slight difference between the previous definition and the present definition. The difference between magnetic field strength is denoted by B and magnetic flux is denoted by phi. So I am writing here, my phi is called magnetic flux, my B is called magnetic field strength or magnetic field induction, in whichever the names we can call it. Therefore phi is equal to B into A, my phi is called magnetic flux and my B is called magnetic field strength and A is called area of cross section. I am writing here where B is equal to magnetic field strength, and A is called area of cross section. If you want to take the SI unit of magnetic flux, we can write like this. Phi is equal to B into E. Okay. Now in the previous definition, that is third definition as we completed in the previous one, my B is equal to phi by A. But here if you take cross multiplication, phi is equal to B into A. That means I can write like this here. B is nothing but called Weber per meter square. Weber per meter square into meter square. So if you cancel this meter square to meter square, both of them, I will get the remaining term is Weber. So we could accept that the SI unit of magnetic flux is Weber. Magnetic field strength is measured in Weber per meter square, whereas magnetic flux is measured in Webers. This is the ultimate SI unit of magnetic flux phi. Now we are going to enter into the precious definitions like magnetic permeability, intensity of magnetization. Let us see now. Now the fifth definition is magnetic field intensity. Magnetic field intensity. It is denoted by capital H or H bar. It is a vector quantity. Magnetic field intensity. It is denoted by the magnetic field intensity is exclusively a ratio of two parameters. One is called force and another one is called pole strength. Let us see this. I am writing the definition. It is defined as the force experienced by a unit magnetic north pole, a unit magnetic north pole, force experienced by a unit magnetic north pole with respect to a magnet is called magnetic field intensity. Magnetic field intensity. It is denoted by H bar. So how do we represent this in mathematical analysis? My H bar is equal to F by M. So in this particular equation, my students, my Hy is called vector quantity, my F is called vector quantity, and my M is called scalar quantity. So strictly speaking here, where F is equal to force and M is equal to magnetic pole strength. Magnetic pole strength. Then how do we take the SI measurement here? Strictly speaking here, my H bar is equal to F by M. We all know that F is measured in newtons. So therefore, I can write it as Newton per ampere meter. Ampere meter. This is called the ultimate unit of magnetic field intensity. Let it be denoted by H bar. That H bar is equal to F bar by M. That is equal to Newton per ampere meter. After computing this magnetic field intensity, now we are going to enter into the magnetic permeability. Let us see this. The sixth definition is magnetic permeability. We have a relationship between magnetic permeability, which is denoted by mu. So I can represent this mu is defined like this. The magnetic field strength or the magnetic induction field, the magnetic field strength is directly proportional to magnetic field intensity. How do we represent that in mathematical notations? B directly proportional to H. So you are seeing two parameters. This B is called magnetic field strength or magnetic induction field, which is called magnetic field intensity. My magnetic field strength is directly proportional to magnetic field intensity. If I want to remove this proportionality, I have to put one constant here. Therefore, V is equal to mu H, where mu is equal to magnetic permeability. Magnetic permeability. This we can also call it as proportionality constant. Whenever the magnetic field strength is a parameter which is directly proportional to the other parameter called magnetic field intensity, if you want to remove this proportionality, we have to put one constant here, that V is equal to how much? Mu H, where mu is called magnetic permeability. But strictly speaking, that if you look at this equation, V is equal to mu H, which is completely in medium. How do we define this? My magnetic field strength is in medium, my magnetic permeability is in medium, and my H is magnetic field intensity is also in medium. So strictly speaking, that this B is equal to BH is a relation which existing in medium. Now we are going to suppose the same relation was expressed in free space. How do we represent this? Let us see this. The relationship between magnetic field strength and magnetic field density was representing in free space. We could represent like this. If B0 is equal to magnetic field strength in free space and H is magnetic field intensity, then in free space the relation is given by, in free space the relation is given by B0 is equal to mu naught H. This is the important equation you have to remember here. So this is completely in free space. So how do we represent that this relation is in free space? Because B0 is equal to mu naught H. As I told you in the previous definition that in the magnetic permeability, the magnetic field strength is directly proportional to magnetic field density. Then if we remove that proportionality, we put a constant that is called mu. Let it be called as magnetic permeability, but it is medium. Suppose if my magnetic field strength in free space is directly proportional to magnetic field density, I could write it as B0 is equal to mu naught H, where this mu naught is called where mu naught is equal to permeability, magnetic permeability in free space. In free space. But it is a constant element. So what is the value of this mu naught? Let us see this. My mu naught is equal to 4 pi into 10 power minus 7 Henry per meter. This is a constant value which is always constant anywhere existing in this. That mu naught is equal to 4 pi into 10 power minus 7 Henry per meter, called permeability in free space or magnetic permeability in free space. Now we are going to enter into the seventh definition, that which is called intensity of magnetization. Let us see this. The seventh definition of basic definitions of magnetism is as follows. Its name is intensity of magnetization. Intensity of magnetization. It is denoted by I suffix M or I. The intensity of magnetization is a ratio between magnetic dipole moment and volume of the magnet. So how do we define this? It is defined as the ratio of magnetic moment per unit volume, and it is represented by I suffix M is equal to M by V. This is the standard definition and mathematical notation for intensity of magnetization. If you look at this definition, the intensity of magnetization is defined as the ratio of magnetic moment per unit volume. Therefore, I suffix M is equal to M by V, where M is equal to magnetic moment and V is equal to volume of the magnet. Volume of the magnet. If we can convert this into pole strength, the product of pole strength with the length of the pole magnet and area of the magnet with the length of the pole magnet. So how could we write this numerator term M and V? I can write like this. If a parallelogram or if you take a rectangular parallelepiped whose length of the pole magnet is 2L and whose corresponding magnetic pole strength is denoted by M, I can write this M as where my ion can also be expressed as m into 2l by a into 2l. And in the numerator term and the denominator term, 2l is there. So cancelling both of them, I will get Im is equal to m by a. Now I define the intensity of magnetization. Im is equal to pole strength per unit area of cross-section. So we can define like that also. So according to the context, my dear students, we have two definitions for intensity of magnetization. That is, intensity of magnetization is defined as magnetic movement of the dipole by volume of the magnet, and this can be also considered as m can be written as m into 2m. In this formula, my m is called pole strength of the ball magnet, and 2l called the length of the ball magnet, and v is called the area of the cross section into length of the ball magnet. Bring both of them and substitute in this equation. I will get Im is equal to m into 2l by a into 2l. As 2l to l cancelled, I can get m by a. So I can represent that intensity of magnetization is also a ratio which can be represented as pole strength, magnetic north pole strength by unit area of cross section. Usually we take magnetic north pole. So how do we like this? Magnetic north pole is like this. So Im is equal to m by e. So strictly speaking, that if you want to write the SI unit of this, I can write like this. How do we like this? That implies ampere meter for meter square. As meter cancelled in one time, I will get the ampere meter. The eighth definition followed by basic definitions is the eighth definition followed by basic definitions is magnetic susceptibility. This is denoted by psi. It's a relationship between the intensity of magnetization with the magnetic field intensity. How do we define this? The intensity of magnetization is directly proportional to magnetic field intensity. That means we can write it in mathematical as I directly proportional to h. If I remove this proportionality, I can get I is equal to psi h and psi is equal to I by h. This is the ultimate mathematical relationship between I and h, where I is called intensity of magnetization and h is called magnetic field intensity. Strictly speaking, my magnetic susceptibility is a dimensionless quantity. It doesn't have any units because psi is equal to I by h because it's a ratio. It's a ratio between two parameters. The first parameter is intensity of magnetization and the second one is magnetic field intensity. Now we are going to enter into the relative magnetic permeability. The ninth definition of basic definitions of magnetism is magnetic relative permeability. It is denoted by mu suffix on. It is also a ratio, my dear students. The magnetic relative permeability is defined as the ratio of magnetic permeability to the magnetic permeability medium to the magnetic permeability in free space. Magnetic permeability in free space. How do we define this in mathematical notations? It is denoted by mu suffix on, that is equal to mu by mu naught, where mu is called magnetic permeability in medium and mu naught is called magnetic permeability in free space. So, strictly speaking, that it is a ratio of magnetic permeability in medium to the magnetic permeability in free space. So, we can represent that mu r is equal to mu by mu naught. Now, we have a relationship between BH and I. Let us see based on magnetic permeability and now relationship between BH and I. The total magnetic dipole moment per unit volume inside a solid is called the magnetization of the material. So, how do we represent that magnetization of the material? The magnetization of the material B is expressed in terms of B naught plus B suffix mu, where B naught is equal to magnetizing field in free space. Magnetizing field in free space, which can be represented as B naught is equal to mu naught H, equation 1, and where Bm is equal to magnetizing field in medium. I can represent with respect to intensity of magnetization that Bm is equal to mu naught I, equation 2. Bring equations 1 and 2 in the above relation, that is B is equal to B naught plus Bm, we can get like this. That implies B is equal to mu naught H plus mu naught I. As mu naught is common in both the terms, I can bring out like this: B is equal to mu naught into H plus I. This is the relationship between magnetic induction field B, magnetic intensity H, and intensity of magnetization. Therefore, B is equal to mu naught into H plus I. Now we are going to get the relationship between relative magnetic permeability mu r and magnetic susceptibility. Let us see now. Relationship between magnetic permeability, magnetic relative permeability, and magnetic susceptibility. We know that, we have a standard relationship between B BH and I, how do we write this? We know that the relationship between BH and I is given by B is equal to mu naught into H plus I. I can call it as equation 1. Now, by definition of magnetic permeability in medium is represented as, by definition of magnetic permeability in medium is given by B is equal to mu H. I can call it as equation 2. B is equal to mu H. Now, I would like to write the definition of magnetic relative permeability as the magnetic relative permeability is given by is mu r is equal to mu by mu naught. From this mu can be written as followed by mu is equal to mu r into mu naught. Now bring the value of mu is equal to mu r into mu naught in equation 2. We will get B is equal to mu r into mu naught into H. I can call it as equation 3. Now substitute equation 3 in equation 1, we will get like this. Substitute 3 in equation 1, we will get mu r into mu naught into H is equal to mu naught into H plus I. Now both sides we will cancel mu naught here. It's a common term which is called magnetic permeability in free space, which is constant. In both sides mu naught is there. I can cancel mu naught here, and the remaining term is mu r into H is equal to H plus I, and mu r is equal to how much? H plus I by H. So we can split this equation as a plus b by 2. That means a by 2 plus b by 2. Similarly, mu r is equal to H plus I by H. That means we can write it as mu r is equal to H by H plus I by H. Let us see this. Mu r is equal to H by H plus I by H. You can get it as again mu r is equal to 1 plus I by H. We can write it as mu r is equal to 1 plus xi, where since xi is equal to I by H, by definition of intensity of magnetization. Therefore, mu r is equal to 1 plus xi. This is what is known as the relationship between relative magnetic permeability and magnetic susceptibility. Mu r is equal to 1 plus xi, and where xi is called I by H, which is a standard definition for the ratio of intensity of magnetization to the magnetic field intensity. The remaining portion of this magnetism will continue in the next class. Thank you very much.